Welcome. This is a video about one-to-one functions and inverse functions. So we're going to start with one-to-one functions. A function is one-to-one if for every x there is one and only one y. Okay? A function is one-to-one if for every x there is one and only one y. One and only one y. So the idea there is the reason they call it one-to-one is if you have one x, you have one and only one y. So there's 1, 2, 1. Okay? And hopefully you remember what functions are. So to be a function, your graph has to pass the vertical line test. And to be a function, basically none of the x values are going to be the same. But a one-to-one function is even more strong than a regular function. Okay, and we're mostly going to be looking at some graphs here and trying to decide whether the graph represents a function that's one-to-one. Okay, so let's see an example. Okay, example. Determine whether each graph represents a one-to-one function. Determine whether each graph represents a one-to-one function. Okay, and for our first example, I'm just going to sketch a graph here. We don't even need to know an equation for this graph. I'm just going to draw a picture for us, and we're going to decide whether that graph represents a one-to-one function. Okay? So the graph I'm sketching here looks something like x cubed. But it's just a sketch that I'm drawing here. So we'll say this is f of x equals x cubed. Okay, so for this graph, we can see that it is a function because it passes the vertical line test. So if you don't remember the vertical line test, basically every single vertical line has to intersect the graph at less than 2 points. So in other words, no vertical line can intersect the graph at more than 1 point. Okay, so to determine whether it's a function, we use the vertical line test. Vertical line test. Now that's not to determine if it's a one-to-one function, that's just to determine whether it's a function. So is it a function? Well, if I look at every single vertical line that I can draw here, for example, if I draw a vertical line there, that vertical line only intersects the graph at 1 point. And if I draw a vertical line over here on the right side, let me get my graph to look a little bit better here. If I draw a vertical line over here, once again, it only intersects the graph at 1 point. So the vertical line test says no vertical line intersects the graph at more than 1 point. No vertical line intersects the graph at more than 1 point. And as we can see here, no matter where I put my vertical line, it's only going to intersect the graph at one point. So that means that this is a function. Okay, so I'll just put a little check there. Now you should know about this, hopefully, but if you didn't remember how to determine if a graph is a function, you use the vertical line test. Okay, now to be a one-to-one function, you have to both be a function and you also have to be one-to-one. Okay, so we checked, and this one is a function because it passes the vertical line test. Now, how do we determine if it's also one-to-one? Well, for each x, there can be only one y. One and only one y. So it has to be a function, which this one is, but you also have to pass a different test. So to determine whether it's one-to-one, we're going to have to do what's called the horizontal line test. Okay, so one-to-one, we have to use what's called the horizontal line test. Now the horizontal line test is basically identical to the vertical line test. The only difference is instead of looking at every single vertical line and making sure no vertical line intersects the graph at more than one point, we're going to be using horizontal lines and asking ourselves the same question. No horizontal line may intersect the graph at more than one point. Okay? So the horizontal line test says no horizontal line intersects the graph at more than one point. Okay, so you got your horizontal line test is basically the same as the vertical line test. You're just going to be looking at horizontal lines now. So this one did pass the vertical line test, and now we can do the same thing but with horizontal lines to determine whether the graph represents a one-to-one function. So if I draw any horizontal line anywhere I want on this graph, we can see, for example, here, this blue horizontal line only intersects the graph at one point, so we're good there. And if I draw one right here, right on the x-axis, we can also see that that only intersects the graph at one point. Even though the graph is getting close to horizontal right there, it's not quite horizontal, so it's only intersecting at one point. And the same thing up here. If I draw another horizontal line up here, none of these horizontal lines are intersecting the graph at more than one point. So that means this is actually a one-to-one function. Okay, so first we checked to make sure it was a function. It passed the vertical line test. And a lot of people like to think of the vertical line test as the pencil test. And you can also call the horizontal line test a pencil test. Because if you hold your pencil vertically, and you determine the number of points where your pencil intersects the graph. As long as your pencil never intersects the graph at more than one point vertically, then it passes the vertical line test. And then the same thing for the horizontal line test. So if you hold your pencil horizontally, if your pencil never intersects the graph at more than one point horizontally, then it passes the horizontal line test. And that would mean that it's one-to-one. Okay, so it's hopefully a pretty simple idea, and most people should be familiar with the vertical line test from other courses. So the horizontal line test is basically the same thing. Now, why are we learning about this stuff? Well, we just determined that the graph is both a function and a one-to-one function. So, so our answer here is it's going to be yes. This is a one-to-one function. Okay, so the graph represents a one-to-one function. A one-to-one function. So to be a one-to-one function, you have to pass both the vertical line test and the horizontal line test. And if you fail either of those tests, you are not a one-to-one function. So for example, if you fail the horizontal line test, that means you're not one-to-one. And then if you fail the vertical line test, that means you're not a function. Okay? All right. So we're going to do one more example, just to make sure we can see an example that's a little different. Okay, so let's take a look at another graph. Okay, so example number 2. For example number 2, our graph is going to be g of x equals absolute value of x. Okay, g of x equals absolute value of x. So I'm just going to do a sketch of this. I'm not going to bother to plot points. If you want a more accurate graph, you can plot points, or you can just use a graphing utility, either an online graphing tool or a graphing calculator, and then it will give you a much better, much more accurate picture. But absolute value of x kind of looks like a V, so I'm just going to do a sketch of a V, and then we'll go with that. Okay, so that's g of x equals absolute value of x. Now we're just going to be focusing on the graphs because many times the easiest way to determine whether a function is one-to-one or whether it's a function is to just look at the graph, as I said, using a graphing calculator or a graphing utility. If you want to do it without a graph, it can be more difficult. But the idea with that is you would have to plug in numbers for both x and y and make sure that for each x you get one and only one y. But that's a little bit trickier, so I would recommend that most people just use a graphing utility or sketch a graph by hand. Okay, so for this one, let's start with determining whether it's a function. So is this a function? Is this a function? Well, we're going to be using the vertical line test. I'll just call it VLT. Well, any vertical line, or also called the pencil test, I can hold my pencil vertically at each point in the graph, and I need to make sure that my pencil never intersects the graph vertically at more than one point. But here we can see on the left side, on the middle, and on the right side, my pencil never intersects the graph at more than one point. So for example, right here, this vertical line only intersects the graph at one point, and same thing over on the right side. This only intersects the graph at one point. So this does pass the vertical line test. Okay, so it is a function. This is a function. So I'll put a little check mark at function. Okay, and then to determine whether it's a one-to-one function, we have to do the horizontal line test. Okay, so one-to-one, question mark. Well, for that one, we have to do the horizontal line test. So for the horizontal line test, once again, easiest way to do it is hold your pencil now horizontally and move it over the graph, and make sure that the pencil never intersects the graph at more than one point. Well, unfortunately here we have a problem. So on this graph, if I draw a horizontal line down below the x-axis, that doesn't intersect the graph at all, so that's still okay. And even up here close to the x-axis, it doesn't intersect the graph at more than one point, so we're good. And even on the x-axis, the horizontal line only intersects the graph at one point, so that's still okay. But once we get above the x-axis, we run into a problem. So up here, a horizontal line intersects the graph at 2 points, which is more than 1 point, which means it fails the horizontal line test. Okay, so that means it's not 1-to-1. So I'll just put an X there to show that it's not 1-to-1. Okay, so this one is actually a function because it passed the vertical line test, but it's not a 1-to-1 function. Okay, so what most people would write is it's not 1-to-1. It's not 1-to-1. All right, and that's going to be my answer. And of course, to be a 1-to-1 function, you have to be both a function and you have to be 1-to-1. Well, this one's not 1-to-1, so it's not a 1-to-1 function either. Okay? Cool. So I think that takes care of 1-to-1 functions. And once again, we can see the reason they're called 1-to-1 is for each x, there is one and only one y. So this first function that we looked at, if you look at each x, we can see from the graph as we go along that y is just steadily increasing as x increases. And at no point in the graph do we have an x giving us 2 y's or a y giving us 2 x's. Whereas in the second example, we see that the problem here is, for example, when x is right here, it gives us it gives us a y there, and then when x is over here, it gives us the same y. So that y actually gave us 2 x's, is what I meant to say. Okay? So that made it not 1-to-1. But the vertical line test and the horizontal line test are best. Those are the best ways to do that. Okay, so now why are we learning about 1-to-1 functions? Why are they important? Well, if a function is 1-to-1, if a function is 1-to-1, oh, didn't have enough room there. If a function is 1-to-1, then it has what's called an inverse function. Okay? It has an inverse function. So in order to have an inverse function, your function has to be 1-to-1. That's why we were learning about 1-to-1 functions. Okay? Now, what is the inverse function? How do you get the inverse function? What does it look like even? Well, an inverse function basically just switches x and y. So you're swapping your x and your y coordinates. Okay? So the inverse function is obtained. So let's call our function f. Okay, so we're going to call our function f. So if a function f is 1-to-1, it has an inverse function. The inverse function, written f inverse. Now I say f inverse, but it actually looks like it says f to the -1 power. Okay, don't take the -1 power too literally. It's just a notation. The inverse function, f inverse is the way we read this. We don't say f to the -1, we say f inverse, is obtained by switching the x and y coordinates. Okay? All right, and that's really all you're doing when you're finding an inverse function. But it should make sense to you that the function has to be one-to-one, because if you're swapping x and y, you need to have exactly one x and exactly one y so that you can swap them with each other. If there was one x and two y's, how would you know which one to swap with? And vice versa, if there were two x's for one y, then once again, how would you know which x to swap with a y? So that's why it has to be one-to-one. Okay, so the inverse function is obtained by switching the x and the y coordinates. Okay, and for us, we're just going to be focusing on finding the inverse function, because in calculus, we are going to be doing derivatives of inverse functions, and in order to find the derivative of an inverse function, they will give you a function, and then you will need to first find the inverse, and then you will need to find the derivative of the inverse. And that's generally the easiest way to do those. There's also a formula, but usually the formula can be clunky, so it's easier to just find the inverse and then take the derivative. But for now, we're going to focus on finding inverses. Okay. And I'll do one sketch of this as well as we're going along, just so that we can see the picture. Okay, so example. Example. Find the inverse of each function. Find the inverse of each function. Okay, so for problem number 1, we want to find the inverse of a relatively simple function. This one is f of x is equal to x to the 7 minus 4. X to the 7 minus 4. Okay, so the inverse function is obtained by switching the x and the y coordinates. And they have already determined that these functions are one-to-one. So they tell us in your instructions that the function is already one-to-one, so we don't have to worry about that. So we don't have to determine whether it's one-to-one, we can assume that. But we do need to find the inverse by swapping the x and the y coordinates. Okay, now keep in mind that f of x at the beginning, f of x is the same as y. So your first step here is to replace f of x with y. Okay, so we have y equals x to the 7 minus 4. Okay, so step 1. Step 1 is replace f of x with y. Okay, that's a pretty easy step, and everyone should know that f of x or g of x or h of x, whatever your function is, that's the same as y. Okay, your second step is to switch or interchange x and y. Because to find the inverse, like I was saying, to find the inverse, all you're really doing is switching or swapping your x and y coordinates. So step 2 is going to be switch x and y. Now you got to be careful here. You're only switching the letters or the variables. You're not switching anything else. So in this step, you're not moving anything around besides the x and the y. Okay, so this x and this y, we're going to interchange them or switch them, but everything else stays the same. So we're not going to move the 7th power, we're not going to move the minus 4 in this step. Okay, so now instead of y equals x to the 7 minus 4, we're going to have x equals y to the 7 minus 4. Okay? All right, now the third step is probably the hardest step. For your third step, what you want to do is you want to actually solve for the new y. Because we've switched x and y, remember when you have an equation, you always want to isolate y. So our third step is to solve for y. This is actually a new y, by the way. This new y, when we solve for it, is actually going to be our f inverse. Okay, so step 3, solve for y. So to solve for y, first of all, we need to get all the terms involving y on one side and everything else on the other side. So for example here, this minus 4 needs to go to the other side. So what we're going to do here is we're going to add 4 to both sides. Okay, so we add 4 to both sides. So on the left side we get x plus 4, and on the right side we have y to the 7. Okay, we're still not done solving for y though, because we also need to actually get rid of the 7th power. So I don't know if you know this, but if it were squared, so the second power, we would take the square root of both sides to get rid of that. But in this case, because it's not a squared, it's a 7th power, we actually want to take the 7th root of both sides. Okay, so that's what we're going to do here. Now, when you're taking an odd root, you don't have to put a plus minus. Okay, so just a little note here. Odd roots don't have a plus minus. Okay, that's only for even roots. When you take the even root of both sides, that's when you have a plus minus. So for example, the square root property, you take the square root of both sides of an equation, you have to put a plus minus on the right side. And the reason that works that way is with any even root, there's always going to be two solutions. One of them is positive, the other one's negative. Because when you take a positive or a negative to an even power, the negative actually cancels out. So that's why you get two answers. Okay, so anyway, just remember, odd roots don't have a plus minus, even roots do. So here, because it's an odd root, we don't have to put a plus minus. So what we got here is on the left side we have 7th root of x plus 4. And then on the right side we have 7th root of y to the 7. Now remember, you just apply whatever root you need to get rid of the power. So because we're taking the 7th root of y to the 7, now the 7th root and the 7th power cancel out. So we just get y. Okay, so that gives us y equals 7th root of x plus 4. All right, now there's just one more step when you're finding an inverse function. So step 4. Step 4 is actually one of the easiest steps. At the end here, once you solve for your new y, that new y is actually f inverse. Okay, so we replace, our step 4 is replace y with f inverse of x. And again, it looks like it says f to the negative 1 power of x, but it's actually read f inverse of x. And that's the inverse function that we got by just switching x and y and then solving for the new y. Okay, so here our answer is going to be f inverse of x equals 7th root of x plus 4. Okay, and that's actually the whole problem. Now, I won't always draw a sketch of the function and the inverse, especially because drawing is hard, particularly on a computer for me. But I will go ahead and do a sketch this time, just so you can see them. Now you don't need to draw anything on your homework, but I just wanted to show you this, so you can see how the function and the inverse function are related. Okay, so for the original function, if I graph the original function, f of x equals x to the 7 minus 4. X to the 7, because it's an odd power, is going to be shaped a lot like x cubed. It'll just be a bit steeper. It'll be a bit flatter around the middle and then steeper around the edges. And then the minus 4 just means that we're going to be shifting the graph down 4 units. So if I sketch f of x, I'm basically just going to be sketching something like x cubed, but shifted down 4 units. So let me give myself a little bit more room down here. And it'll be like x cubed, but it'll be more steep. So I'll go ahead and do f of x in red here. So it'll look something like this. It's got to be steep because x to the 7 is a pretty large power. And around the middle it's going to be very flat. And again, this is just a sketch. You can always use a graphing utility if you want to get a better picture. Okay, but that's a sketch of our f of x. That was the original function we started with. Okay, and then for our f inverse of x, we have 7th root of x plus 4. Now the shape of that is basically going to be the same shape, but it's going to be reflected over the line y equals x. Okay? So it's going to be reflected over the line y equals x, which is up here. Y equals x. Now the reason it's reflected over that line is because when you switch x and y, that means the y and the x get switched around. So that ends up, when you switch all the coordinates, you're basically just reflecting every single point over that line. So it's basically going to be the same graph, it's just going to be sort of rotated, and now it's going to be centered on the x-axis instead of the y-axis. And it's going to be going to -4 on the x-axis instead of -4 on the y-axis. So it's going to be that same exact shape. I'll go ahead and sketch it in blue. It's going to be that same exact shape, but it's going to be sort of rotated. And it's going to be rotated by about, well, not by about, but by 90 degrees. By exactly 90 degrees. Okay, so it'll look something like that. And again, that's just a sketch. Not perfect, but you know, we get the idea. Okay, so that's a sketch of f inverse. So you're not going to be doing graphing with these, so I'm just going to do it with this one, just so you can see it. But the idea is f inverse of x is obtained from the graph of f of x by reflecting the graph of f of x over the line y equals x. Okay, so f inverse of x is obtained from the graph of f of x is obtained from the graph of f of x by reflecting over the line y equals x. And ultimately all that means is, like I said before, you're just switching x and y, and when you switch x and y, you get exactly the same picture, but sort of rotated by 90 degrees, and it's up here on the x-axis now, instead of on the y-axis. Okay? Cool. But the graphing part won't be that important for your homework, it's just good to know about. So that's number one. And then we just need to do a couple more examples of finding an inverse function. Or maybe one more example would be good. Let's do one more example of finding an inverse function. Okay, so example number two. Example number two. For this one, our function is going to be g of x is equal to x plus 7 quantity squared. G of x equals parentheses x plus 7 parentheses squared. And here they say something different. They say x is actually greater than or equal to negative 7. X is greater than or equal to negative 7. Now, why do they have to say that x is greater than or equal to negative 7? The reason is, the reason they're saying this here is they have to restrict the domain in order to make the graph a one-to-one function. So the reason they're saying this x is greater than or equal to negative 7 is so the graph is one-to-one. Oops, my eraser's not working. Okay, there we go. So graph is one-to-one. So they just restrict the domain to make sure that it passes the horizontal line test. I don't really want to sketch that, but if you wanted to, you could type this into a graphing calculator, and you would see that if you didn't restrict the domain, it wouldn't actually be one-to-one, because it would fail the horizontal line test. But when you're actually finding the inverse, this bit doesn't matter that much, okay? So you're still just going to be following the same steps we did on the other problem. It's just this time it's called g of x instead of f of x. Okay, so our first step is to replace the g of x with y. Okay, so we have y equals x plus 7 quantity squared. Okay, so there's step one. Pretty easy first step. And then our second step is going to be to switch x and y. And we're only switching the letters, we're not moving anything else. So we just switch x and y, the letters x and y. Okay, so we get x equals the quantity y plus 7 quantity squared. Okay, and then we move on to our third step. So our third step is to solve for the new y. And remember, x is greater than or equal to negative 7, but we're not really going to worry about writing this in until the end of the problem. Okay, you don't have to keep writing it in at each step. So we're just going to be following the steps we did in the last problem. So now here, to isolate y, you would not want to square this out using FOIL. That would be a pretty bad idea, because then you would have a polynomial on the right side in y, and it would be difficult to solve for y. So the smart way to solve this is actually to get rid of the square first. And to get rid of the square, the easiest way to do that is to take the square root of both sides. Now for the square root, because it's an even root, we actually have to put a plus minus in front of it after we take the square root. So if I take the square root of both sides, then I end up having to put a plus minus, and I'm going to put the plus minus in front of the root x. Okay, and then on the right side, the square root and the square are going to cancel out. So we get y plus 7 equals plus minus square root of x. Okay, y plus 7 equals plus minus square root of x. And then we're still not done solving for y yet, so we have to get rid of the plus 7. So to do that, we're going to go ahead and subtract 7 from both sides. Okay, so that gives us y equals negative 7 plus minus root x. Or we can write it as plus minus root x minus 7. Now you might think that was the whole problem, right? But the only thing that's a little trickier about this one is, remember, our domain was originally restricted. So originally we said x had to be greater than or equal to negative 7, and they said that so that the graph was 1 to 1. Now it turns out if you have a function like that, in most cases, at the end here, your inverse function is also going to have a restricted domain. So for example, with this one, we can replace our y with g inverse of x. So at the end we have our g inverse of x. But the tricky part is you don't actually want to have a plus minus in your answer. I know that sounds a little bit strange. But here we only want to have a plus. So I'm just going to circle the plus here. So we just have plus root x. Okay, so we have positive root x minus 7. Now you might be wondering, well, why is it just the plus? What happened to the plus minus? Well, it turns out that we don't need the minus. Because if we had a minus here, then x would actually be smaller than negative 7. Okay, so I know that sounds a little bit strange, and if you look at the graph, it might make more sense to you. I'm not going to sketch a graph this time, but if x is restricted to being greater than or equal to negative 7, then that means that we can't have a negative root x here, because that would actually be getting smaller than negative 7 over here, because this is negative 7 and then it would get smaller. So anyway, you're just going to be circling the plus here. Okay. Alright, so we got root x minus 7, and then we still have to write a restriction on the domain. So how do we know how to restrict the domain? Well, here, because the square root is around this new x here, remember that radicals, you can't take the square root of a negative number because it gives you I, which is an imaginary number. So what that means is what's inside of this radical here can't be negative. Okay, so this x here can't be negative because the square root of a negative number is not a real number. So that means that at the end here, for our new inverse function, that means x has to be greater than or equal to 0. It's okay for it to be 0 because you can take the square root of 0, but it can't be negative because the square root of a negative number is imaginary. So since it can't be negative, x has to be greater than or equal to 0. Okay? And if you aren't sure whether you did it right, what I recommend is that you actually use a graphing utility and you graph this original function. If you graph this original function and you restrict the domain so that x is greater than or equal to negative 7, and then you graph your inverse, you'll be able to see that if you graph the negative root x minus 7, it wouldn't have the correct shape. It wouldn't actually be the shape reflected over the line y equals x. So that would be another way you would know that you have to do the plus and not the minus. But it has to be one or the other. It would have to be the plus or the minus. It can't be both, because otherwise it wouldn't be a one-to-one function. So that one's a little bit trickier, I know. But once you get past the little technicalities of the restricted domain and then dealing with the plus minus, hopefully it's not too bad.